Okay, Chem 30, I'm going to try to make this the last lecture. What I want to do before I finish up titration curve and then talk about titration problems, because the last little bit is about buffers, what I want to do is I want to go to page 754 and page 755 in your textbook. So you can turn there. You can stop watching the video and turn there. And I want to do question number 2. Because I was talking about indicators and how they're weak acid, weak base conjugates. So if we look at question 2, I just want to do a couple examples that look like this, because it'll reinforce what I'm going to talk about with buffers and picking out the appropriate, indicator for different titration curves, all right? So question 2 says, first and foremost is a little blurb on page 754 that says, use this information to answer questions 2 through 4. According to the Bronsted-Lowry concept, acid-base indicators are simply colored conjugate acid-base pairs. As for all other weak acids, the conjugate acid forms of these indicators must differ in strength for different entities. Okay, so the question says, for each indicator following, write a Bronsted-Lowry equilibrium equation for the reaction of the acid form of the indicator with water to form a hydronium ion and the base form of the indicator, and use the same indicator symbolism as used in the table of acid-base indicators on the inside back cover of the book or in your data booklet. Your data booklet with indicators is on page 10. Okay? And label all entities as acid or base. So I'm going to do the first 2. So this is on page 755. And the first one is methyl orange. All right? So this is page 755. And this is A. This is methyl orange. Okay, so it's going to react with water to form a hydronium ion. So here's the deal with these acid-base pairs. So methyl orange is HMO plus water. Okay, and this is a weak conjugate acid-base pair. And you actually have Kas, right, for your, so on page 10, you have Kas for your acid-base indicators as well. So you have acid ionization constants and you have base ionization constants, because you can find the Kb by the relationship of Ka to K and Kb to Kw. Okay? So this is going to make MO negative, and that's also on your acid-base chart, plus H3O plus. So this is my indicator. So this is my indicator combination. Now, when I look at methyl orange, the range is 3.2 to 4.4. Okay? Now, if it's 3.2 or lower, it's red. And again, I'm getting this from my acid-base chart. And 4.4 or above is yellow. Now, so in between, that's going to be orange. So I'm going to use methyl orange for like a titration with a strong acid and a weak base. Okay? Because the pH neutralization point, so the equivalence point, is going to be below 7. Alright? So I would use this for a strong acid, weak base titration curve. Alright, now, so let me look at some equilibrium shifts here. So let's say we add HCl to this, and this is an indicator. So I know that HCl is a big 6 acid, so that's H3O plus. So if I were to add H3O plus, the equilibrium would shift this way and turn red. Okay, and my new equilibrium would be this. Okay, so as a result, because of the weak acid base conjugate, right? So there's my weak acid, that's H2O. This acts as the base in this case, and then this ends up being the weak base, and then that's my acid. All right, so this is the conjugate acid and the conjugate base. So in an acidic solution, if we were to add a greater level of acidity, because of the equilibrium shift away from the hydronium, the solution turns red. All right? Now, if we add NaOH, or OH negative, right? It doesn't necessarily need to be sodium hydroxide. It could be calcium hydroxide or anything else that has OH negative. All right? What happens is the H3O plus reacts with the OH negative, right? And that makes H2O. So what this is seen as, so the stress on this is seen as a decline in H3O plus. All right? So that's my stress. Now what happens is if methyl orange is in a basic solution, it shifts towards the hydronium because the hydronium, it has a deficit, right? My new equilibrium is here. So what happens is as basicity increases, the hydronium is neutralized. So the equilibrium shifts towards the hydronium, and the hydronium turns the equilibrium reaction yellow. Okay? So acid-base indicators work on the principle of equilibrium shifts. All right, so it's nothing that you haven't seen before. It's just a different way to look at it. I'll do one more, and I'll do this. I'll do B. B is indigo carmine. Okay, so indigo carmine, it works best in a pH of 11.4 to 13. So again, I'm looking at my acid-base chart. And this is HIC plus water. And it's going to have a weak acid-base pairing. This makes IC negative plus H3O plus. All right, now, again, this pH works, this indicator works best in this pH. So if we are 11.4 or below, it's blue, and 13 and above, it's yellow. So in between, so if it's like a pH of 12, it's going to be green. So where would I use this? I would use this in a titration with a strong base and a weak acid. So the neutralization point will be well above 7. This would probably be a very weak acid, by the way. Okay? So let's say I add H3O plus. Okay, again, this goes here, this moves up. So the stress shifts that way, the equilibrium shifts that way from the shift. Okay? So my stress is add H3O plus. Okay? The solution would be, right, so the solution turns blue. Alright? Now if we add OH negative, again it's going to react with the hydronium, and that's going to be seen as a hydronium deficit from the perspective of the equilibrium system. Sorry, I should change that. No, that's correct. Turns blue. So this turns, so with increasing basicity, right, the H3O plus is going to be taken out of solution if we add OH negative. With increasing basicity, it shifts to the right and then turns yellow. Okay? So indicators work on weak conjugate acid base principles. So, by the way, this is how we do things like determine the pH of pool water, right? So if we're gonna, right, so over time what happens to pool water is as the public uses it, the pH declines, right? And that's because people pee in it. Like, that's actually why, right? So when we're testing, so we test basic bacterial count, but we're also testing pH. So if we have, right, so it works on this weak acid-base conjugate. So from urine, you get levels of hydronium because of the urea, or the uric acid, all right? And as the pH declines, we'll be able to tell that. And that will tell us when we need to treat the water again, right? Okay, so just keep that in mind. And keep that pool water analogy in mind as well, because that might come back on a unit test. Hint, hint, wink, wink, nudge, nudge. All right, so that's indicators. The next major focus of titration curve is the buffer. All right, so you need to watch this lecture before you do the buffer lab that I recorded this morning. Okay. So we have two different definitions for a buffer. So a buffer, from a theoretical perspective, is a solution consisting of a weak acid and its conjugate base, so that should say base, in approximately equal concentration. So as a result, you have a weak acid, weak base conjugate relationship, and they make an equilibrium system. So they are present in solution. Here's the deal though, they're present in quantities much less than the solvent, whether that's water or alcohol or whatever. The solution, the buffer itself, okay, here's the deal. The buffer resists the addition of hydronium or hydroxide. So the pH itself is not altered to the degree that it should be, all right? So buffers resist pH change. So they resist equilibrium shifts. So from an empirical perspective, so what we can see from an observational perspective, a solution that's capable of absorbing small amounts of strong acid or strong base with only a small change in pH. That's a buffering system. All right? So it's produced by mixing a weak acid solution with a weak acid salt in general. A buffering region on a pH curve is where both weak acid and conjugate base are present in generally equal amounts. So the shifts are resisted either way. And again, when I did the hydrogen phosphate sodium hydroxide buffer lab earlier today, that's exactly what we saw, all right? The buffer solution resisted the pH change and the NaCl control did not. So here's the deal. From an observational perspective, the buffering region is about halfway between the original pH and the equivalence point. So you have about a 1-to-1 weak acid conjugate base ratio, and the pH change will be resisted here according to Le Chatelier's principle. All right, so I'm going to do a couple examples here. Specific to buffers, and then I have two questions based on titration itself. We'll do a titration question related to this, and that'll be it for this unit. All right, so let's look at this. So this is a titration curve for titrating 0.300 mole per liter acetic acid or ethanoic acid. The common name for that again, right, is vinegar, with 0.300 mole per liter NaOH. So that's going to be hydroxide, OH negative, with a weak acid. Okay? So what do I have present? Now, again, this is being titrated with that, right? So that's my sample, and that's my titrant, and we're going to do the same thing that we do for every titration curve question. We identify the entities that are on my acid-base chart. So that's on my acid-base chart. And then I break up the OH negative, the NaOH into ions, and then I have H2O as well. That's my base, that's my acid. So what's my equation? It's OH negative plus CH3COOH. It makes H2O plus CH3COO negative. So, draw my graph. So this is a weak acid and strong base. So here we have pH. Now this is a weak acid and strong base. So when we look at equivalence, equivalence is above 7, right? And then the end point would be a little bit above that. Okay, so here's where my buffering regions are. So it's a relatively flat curve. So there's a buffering region here. And then there's a buffering region here. So we're about to have a rapid pH change, but the pH change is being resisted here. And my buffering region here is CH3 and COOH and O negative, because those are the entities that are present. And then here, this is CH3, COO negative, and H2O. Okay, so that's where the buffering regions are on the graph. Okay, so you need to be able to pick those out. How much time is left on the camera?
41 minutes.
Okay. What about the charge?
29 minutes.
Was that?
29 minutes.
Okay. That should be it, guys. That should be enough time to get this all done. Okay, so the 5-step method can be used. So this is my next example. Can be used to obtain a Bronsted-Lowry equation to explain the action of the buffer. Okay, so let's say we have these entities in solution. We have, again, this is Na+. So I'm going to use the same entities from the titration curve. Okay, so at some point along this titration, we have these entities that will be present. And H2O. So again, this equation from, this is my weak acid and my strong base. And what ends up happening is I have a weak conjugate and then a weak conjugate base and a weak conjugate acid. Okay? So, here is why the buffering system works. So if I add hydroxide, the system shifts away from the hydroxide. And so if we add OH negative, so this is 1, the system favors the weak base. So the CH3COO negative has a much weaker Kb than the hydroxide, right? So as a result, there'll be less base solubility, all right? So if we add hydroxide, we favor the weak conjugate, all right? Now, if we added hydronium, Okay, so let's say we added hydronium, so add H3O plus. Right, the OH negative would drop. Right, because the H3O plus and OH negative would react together. And so this would drop and the equilibrium would shift towards the weak acid. So as the strong acid is added, we actually favor the side with the weak acid. So this has less solubility, right, because it has a smaller Ka. So this makes less hydronium ion than actually adding the hydronium. Okay? So we favor the side with the weak acid, and that resists the large change in pH. All right? So we always have weak acid-base conjugates as buffers. Okay? So let's look at this one. This says given a HF, so a weak acid base conjugate solution. This says write the Bronsted-Lowry equations and graph to explain the action of the buffer if a small amount of strong acid is added. So let's do that. So if we have HF reacting with H2O, this makes hydronium an F negative. So let's say we add a small amount of strong acid. All right, we shift towards the weak acid. So that's my strong acid, and that's my weak acid. Okay, so we shift towards the weak acid. So shift to the weak acid. Okay. Now, let's say we add a small amount of strong base. Well, the opposite would happen, right? We shift, right? So the OH negative and H3O plus react together, and we shift towards the weak base. Okay, so as strong base is added, equilibrium shifts to the weak base. All right, so either way, strong acid is added, the equilibrium shifts towards the weak acid. Strong base is added, the equilibrium shifts towards the weak base. And that's how buffers work, okay? I'll let you guys take a last minute look at this one on the bottom here. Then we're going to put this down. Okay. So, where am I going to see this? So we talked about this. Buffering capacity, page 766, numbers 18 through 21. Okay, and page 767, numbers 2 through 10. So there's a limit of the ability of a buffer to maintain pH. So once the conjugate acid-base pair that reacts with an added entity is completely consumed, buffering fails and pH changes dramatically. And now where do I see that? If I see that on the graph here with a quick change to equivalence. So once the buffering capacity is overcome, then the pH changes really, really rapidly. So this buffering region resists, and then boom, it changes almost instantaneously. Okay? So you need to be able to figure out where the buffering regions are and where the buffering, so where equivalence is at is where the buffering is overcome. So I'm going to go back to Bio 20 here now and show you a biological system that uses this. So this is carbonic acid buffering. All right, so if we go back to lactate fermentation, right, where we are undergoing anaerobic glycolysis because we're in anoxic conditions. So either A, we're working above our aerobic capacity from a physical standpoint, or we're in an area where there's not enough oxygen. What happens is we can't use, you remember, right, we can't use oxygen as the final electron acceptor in the electron transport chains to make ATP. Right, so what ends up happening is we use the cytoplasm to do that, and the waste product is lactic acid. Now, your level of acidity in your bloodstream is actually measured as carbonic acid. So that CO2 buildup that happens from lactic acid fermentation actually ends up getting dumped into your bloodstream. Okay? Now, that waste product changes the pH of your bloodstream. And we have to maintain a pretty delicate balance there. So we have a buffering system in our blood that helps deal with that. And that's your carbonic acid buffering system. Okay? So, as CO2 gets dumped into your bloodstream from anaerobic glycolysis, all right, you have this enzyme called carbonic anhydrase, and it reacts to create carbonic acid. Okay? The carbonic acid is unstable inside your bloodstream and creates HCO3 negative, which is hydrogen carbonate ion, which is a base, right? So that acts as a buffer, and hydrogen. The hydrogen is bonded to your red blood cells. The hydrogen ends up bonded to hemoglobin. And then we take it out of solution so it doesn't affect acidity, and then the hydrogen ion moves through your bloodstream to your lungs, and we reform this H2O and blow off the CO2 and H2O together. So this CO2 creates competitive inhibition in your hemoglobin. Right? So we don't want this. It's toxic. So we get rid of it by creating carbonic acid, and then the carbonic acid creates a base, which is a buffer, and the hydronium ends up in the hemoglobin on your red blood cells. Okay? So that is your carbonic acid buffering system. And this deals with lactate fermentation. Okay? So the buildup of carbonic acid lowers blood pH, causing homeostatic problems. This comes from carbon dioxide diffusing into the bloodstream as a waste product of anaerobic cellular respiration. Right? So if I'm any type of aerobic athlete, this is why we train, to increase our oxidative carrying capacity. Right? So I can delay the amount of time it takes to go lactic. Right? If I don't have a good system of oxygen transport, then I switch over to anaerobic fermentation sooner. Right? So at a sooner or at a lower rate of exercise intensity. So hemoglobin acts as a buffer. So the hemoglobin bonds. Hemoglobin is, there's 4 little hemoglobin molecules on your red blood cells. The hemoglobin takes this hydrogen and bonds it, moves it to your lungs. This acts as a buffer because it's a base. It could be a base or an acid. But in this case, it acts as a base because it's a hydrogen acceptor. All right, so we neutralize the carbonic acid. Carbonic acid is unstable. It dissociates into H plus and HCO3 negative ions. H plus dislodges oxygen from the hemoglobin. Hydrogen combines with the hemoglobin. And then we remove this H plus, so it doesn't make hydronium in your blood plasma. And the HB buffers hydrogen out of the blood. Okay, so you guys, if you took Bio 20 with me, you saw this slide. Cells, extracellular fluid, this is the cell membrane. Okay, so HCO3 negative ions are transported into the plasma as H plus is removed by hemoglobin, decreasing blood acidity. In lungs, the oxygen dislodges H plus from HB binding sites, so the oxygen can go to the cells now. And then in the lungs, we reform the H2O and CO2 initially from the cells. So we reform it, so we break it up so this stuff isn't hanging out in our cells. We break it up and then reform it in the lungs. And that's why your main waste products from respiration are H2O and CO2. So this happens in the alveoli of the lungs, and this helps resist pH change. All right? So you have to answer carbonic acid buffering in your buffering lab. Okay? The last piece of this unit is acid-base titration stoichiometry. It's really similar to stuff we did in Chem 20. I'm just going to add on to it. What I'm going to do is I'm going to turn this lesson off and do this as a separate, smaller lesson. So we'll sign off now.